Okay, so I'm not, although this is in the benzene topic, I'm not actually going to mention benzene in this video, but I'm going to talk a bit more about electron delocalization. Now we know in benzene the reason why you get delocalization is because I draw benzene sort of sideways on. Formally you've got a double. We can think of it as double single bonds alternating. You've got unhybridized p electrons on every single carbon, and so they can overlap to form a delocalized electron system, which spreads above and below the molecule, the plane of the molecule. And we've seen that in the very first video, and so we said with anything with an alternate single double bond structure. So for example, butadiene, I won't draw the whole thing, but you get electron delocalization there. But if you've got a gap of 2 carbon atoms, so saying if we had pentadiene, you don't get delocalization. In the top case, yeah, these electrons can overlap because the distance between these 2 carbons here is only the same as the others. It's a 1 carbon bond distance, so they can overlap. And those p electrons here, they can't because you've got a gap of 2 carbons. So you just get 2 separate pi bonds forming there. We've had a look at that. Okay, so let's have a look at some other structures. And the electron delocalization occurs in an awful lot of organic molecules. So let's have a look at that. Now this one here, you may have seen it in a much earlier video. We're talking about EZ isomerism. That is vitamin A. And you can see, let's see, where have you got unhybridized p electrons? You've got them on that one, that one, that one, that one. Okay. And so you have a massive delocalized system here. Okay. And over most of the molecule. So and then let's have a look at this thing. It's called Arachidonic Acid. Okay, it's a fatty acid. So you've got your carboxylic acid group on this end here. And you've got a long chain of it's actually 20 carbons long if you count them up. It's polyunsaturated because it's got 4 double bonds in the molecule. Now let's think if electron delocalization can occur here. So we've got p electrons there. So we won't draw it like that. There and there, and there and there. Right, now you can see that they are not going to conjugate to form a delocalized system because there's a gap here of 2 carbon bonds. Same here, 2 carbon bonds here, 2 carbon bonds here. So each of those is a separate pi bond, no delocalization there. And if you're wondering why it's drawn around in a circle like that, well, you can see probably that all of these bonds are all in the Z configuration because that's going to be hydrogens on that side there. Both hydrogens on the same side there, and so on. They're all in the Z, and that has quite an important effect on the shape of it. It makes it form a circle. Right, let's talk about delocalized systems. Then we've only talked about with carbon, but it actually occurs when you've got oxygen and nitrogen sometimes. So I'm going to just have a look at. I can go up here. There's more room. Right, let's have a think about carboxylic acids and alcohols. Now, we know, here's ethanol. I'll draw it like this. Okay, I'm going to draw the OH, so you can see, and then here's ethanoic acid. Now, we know that ethanoic acid has a tendency to lose, it's an equilibrium reaction, has a tendency to lose this H plus here. It's not a very strong acid, but some of them do that. Whereas if you look at ethanol, we know that that's not acidic at all. If you have a solution of ethanol, it's pH 7. why doesn't this occur? Well, that does not occur. And the reason why is because, right, you'd end up with a negative charge just on the oxygen, concentrated on one atom, and that is not, it's not very stable. So it can't do that. It'd have too much negative charge on one oxygen. But let's think what happens here. Now, it's not immediately apparent from this, but right, you do have unpaired p electrons here, and unpaired p electron, sorry, not unhybridized p electrons, should say, and you also have unhybridized electrons on that oxygen there, which wouldn't be immediately apparent, but they are. So that means that these, you can have a delocalized system forming there. Yeah, so you'd end up, right? So that means effectively this negative charge here, which we think of as, we draw as being on one oxygen, that is actually spread out over, well, it's actually not on the carbon, for reasons don't worry why, but it's actually spread out. It's shared between those two oxygens, and that is why this is more stable. So that means ethanoic acid is, so the carboxylic acids are acidic, whereas alcohols are not acidic. Which is interesting. We have a little think about this molecule here, which is vitamin C. Now, you may be aware that the chemical name for vitamin C is ascorbic acid. Okay, so you've got an OH there. I'll draw it as a proper OH displayed. So that is the structure of vitamin C. It's called ascorbic acid. Now you can see it doesn't have a carboxylic acid group on it, but it's about as strong as an acid as ethanoic acid is, and that's because this proton here tends to, it can be lost. So if you lose that proton there, you end up with a negative charge on that oxygen. But the negative charge is not just stuck on that oxygen, it can spread out. Now, as you said before, there's actually unhybridized p electrons on that oxygen there, even though it's not obvious it is. This one, you know there is unhybridized p electrons, there's a double bond, and that one, unhybridized p electrons there, and there's also unhybridized p electrons on the oxygen. So that means when this negative charge here can actually be shared over the delocalized system, which means the negative ion is more stable, and so it is acidic, and that's ascorbic acid. Likewise, we have a little think about when you have an alcohol on a benzene ring. Right, you don't call it an alcohol anymore. It's not on the specification. It's called a phenol because it modifies its behavior. Having the OH stuck onto the delocalized system modifies its behavior quite a lot. And phenols are slightly acidic. They're not as acidic as carboxylic acids, but they are acidic. Because if you lose this proton here, what can happen is, right, where have we got our unhybridized p electrons? We've got them on each of the carbons. So I've finished drawing this. On each of the carbons. And we've also got them on this oxygen here. So that means the negative charge can be partly shared into the delocalized system, the benzene ring. So phenol is a little bit acidic. So phenol, if you try and dissolve it in water, it's insoluble in water, pH 7. But if you put it at pH 14, it forms this negative ion quite readily. And of course, ions, charged things tend to be soluble in water. So anyway, the important thing is that H is a little bit acidic because the negative charge on the oxygen can be shared over the whole benzene ring. So just a few more examples to give you a feel of how important electron delocalization is.